Now that we understand, we understood the problem of the small world effect and what is it that is asked of us, and second, that we formulated it cleanly as a graph theoretic problem where the input is a graph, the output is a distribution of the pairwise distances, we move to the third step, which is designing the algorithm. In algorithmic thinking, again, the third step is designing the algorithm. So now the question is, how do we come up with an algorithm that will compute distances between every pair of nodes? Okay, and we will start with the first attempt, which I would argue is probably the first attempt that anyone would make at such a problem. Since we have defined what distance means in a graph, we can just follow that definition and try to turn it into an algorithm. Remember, the definition said that the distance between two nodes, I and j, is the smallest k for which there is a path of length k between these two nodes, the smallest k. Again, since we don't allow self-loops, we are usually looking at the smallest k of 1. If I have two nodes that are different, the smallest distance between them can be 1 because they can be connected by an edge. So here's the simplest algorithm that probably anyone can come up with. Given the two nodes I and j that are different, first, ask the question, is there a path of length 1 between them? If the answer is yes, we know that is the distance between them. We can return 1 and say the distance is 1, we are done. If no, if the answer is no, then we have to increment that k and say, is there a path of length 2 between I and k? If yes, since there is no path of length 1 and there's a path of length 2, then the distance is 2, we can return 2 and we are done. If no, then we ask, is there a path of length 3? If the answer is yes, we say the distance is 3, we are done. If no, we try 4. And so on. And here's the algorithm. So our first problem in this course, here's a very simple algorithm. I would say that it is very easy to argue that it is correct because I'm just following the definition. Someone defined the distance to me as the smallest k for which there's a path of length k. I'm going in a brute force manner, and I'm trying to check every possible k, starting from 1, going to 2, to 3, to 4. So the algorithm is very simple to describe. It is very simple to implement, I would argue. And it's clearly correct, right? So the question is, am I done? Can I start implementing this algorithm? The problem with the algorithm we just described is, what is the maximum value of k that we should try? So I try a path of length 1, the answer is no. Then 2, the answer is no. Then k equals 3, the answer is no. And I keep incrementing. Am I gonna eventually hear a yes? Is it always the case that if I give you a graph and a pair of nodes in the graph, that this algorithm will eventually find a k such that there is a path of length k between these two nodes? Now, why is that important? In this course, we would want to use algorithms that eventually terminate. I'm not interested in any algorithm that might run forever on some instance of the problem. So I need to guarantee that my algorithm terminates on whatever input I give it. So again, I give the algorithm as input a graph and a pair of nodes, and I say compute the distance. It goes through this repetitive iteration of checking if there is a path of length 1, 2, 3, 4, and so on. And again, the first question I asked, is there always a path of a finite length between any pair of nodes? And the answer is no, because here's an example of a graph. If we follow the algorithm we just described on this graph and the two nodes 0 and 3, for example, the algorithm is going to say, is there a path of length 1 between 0 and 3? The answer is no. Then the algorithm says, is there a path of length 2 between 0 and 3? The answer is no. Is there a path of length 3? The answer is no. 4, no. 5, no. And in fact, there is no path of any finite length between 0 and 3. So the question is, where do we stop? When do I stop and say, no, there is no path of a finite length, or that the distance between 0 and 3 is infinity? If we use mathematical skills here, we can reason about it and get to the conclusion that if I have 4 nodes, then if there is a path between 0 and 3, that path the length of, I can always find a path whose length is at most 3. Okay? So if there is, again, a path between 0 and 3, its length has to be, there has to be a path whose length is at most 3. Or, more generally, if I have a graph with n nodes, and I take any 2 nodes from the graph, if there is a path between these 2 nodes, I can always find a path whose length is at most n minus 1. I encourage you to think about why that is the case. And this is our first encounter of why math and math skills are very important when we design algorithms. We cannot really decouple the two. We cannot say we want to study only algorithms, we don't care about math. We have to use mathematical tools to be able to design a good algorithm. So in this case, there will be cases, inputs, for which there is no path between a pair of nodes, which means that if I continue with that algorithm, I will never terminate. I have to put a bound at which I can be certain that there is no path at that point, and I can say, no, there is no path, and the distance is infinity. Using some mathematical reasoning, I can get to a point where if the graph has n nodes, I can say, try n minus 1 at most, a path of length n minus 1. If you fail with 1, 2, 3, 4, all the way to n minus 1, you can terminate safely and say there is no path of length, of any finite length, and the distance is infinity. Okay? Now, the last question we have to answer is that when I say, is there a path of length k between a pair of nodes? How do I check that? How do I check if there is a path? Let's now look at this graph here. And I say that my question is there a path of length 2 between nodes 0 and 3, for example? Of course, the answer is no. If I look at nodes 0 and 3, there is no path of length 2. But how do I check this? How does a computer program and how does an algorithm test this? Now, notice that we go back to the definition. How did we define distance? How did we say a path of length 2? We said if we are looking at path of length 2, it basically, if you go back to the definition, it says, is there a node that I can put between these 2 nodes, 0 and 3? If I take 0 and 3, can I put some node here such that there is an edge from 0 to this node and an edge from this? Because if there exists such a node, then this path between 0 and 3 exists. What node can this be? I don't know. We can try each one of them. I can put 0, 1, 2, 3. Is there a path from 0 to 0, then 0 to 3? No. 0 to 1, 1 to 3? No. 0 to 2, 2 to 3? No. 0 to 3, 3 to 3? No. Therefore, we say that there is no path. So how do we, again, without thinking too much, how do we check if there is a path of length k between 0 and 3? The idea is very simple. Going back to the definition, it tells me check if there is a subset of k minus 1 of nodes such that there is an arrangement of them between these 2 nodes that will make a path appear. Okay? So mathematically, I can say if you have a node, a pair of nodes, and you want to check if there is a path of length k between them, try every possible subset of k minus 1 nodes, and try every arrangement or permutation of these k minus 1 nodes, and put them in between. So try every subset of k minus 1, and for each one of these subsets, try every possible arrangement or permutation of them. If you get to a point where you could find these k minus 1 nodes, and could arrange them in such a way that there is an edge between every pair of consecutive one, you say, yes, there is a path of length k. If you tried every subset of size k minus 1, and if you tried every permutation of every subset, you still couldn't find a situation where you have an edge between every consecutive pair, then at that point you say there is no path of length k. And as we said before, you wrap this procedure by another layer of looping over k from 1 to n minus 1. You first try k equal 1, then 2, then 3, and you can go all the way to n minus 1. If you find any such thing on the way, then you say, yes, here is the path and here is k. If after trying k equal 1 and 2 and 3 all the way to n minus 1, and you failed, then at that point you can terminate, the algorithm can terminate and say there is no such path or that the distance is infinity. The pseudocode or the description of this algorithm is given in its entirety on the slide. This algorithm can be applied then to every pair of nodes and will compute the distance between every pair of nodes. The nice thing about this algorithm is that it is very easy to describe. It is very easy to implement. It belongs to a category of algorithms that we call brute force. It's an algorithm that literally follows the definition of the problem to try to solve it. It is, again, as I said, it is often the first technique that we try when we encounter a problem for the first time. The brute force algorithms are, as I said, easy to describe, easy to implement, and it's very easy to argue that the algorithm I described is correct because it's just following definition. It's trying every possible key and every possible subset of size key and every possible arrangement of that subset. So I'm not missing anything. So it's easy to establish the correctness and implement it. What is the problem with that algorithm or brute force algorithms in general? The Achilles heel of brute force algorithm is usually efficiency. If you think about this, or if you implement this algorithm and you start running it on Facebook graphs, if you run it on a Facebook graph that has 5 nodes, it's going to give you results. However, as the size of the graph starts growing and you start running it on graphs or networks of size 10 individuals, 20, 50, 100, before you reach 100, before you reach 50, you will notice that this algorithm will take years and years to run on that data. So the good thing about brute force algorithms is easy to implement, easy to argue about correctness, easy to describe. The major problem with them is efficiency. And this brings me to our next topic, which is algorithm efficiency. How do I analyze the running time of this algorithm and show that it is actually not efficient and it's not worth implementing?